Getting there, Give me my 8 minutes. Okay. So that means here, right, I'm going to combine, and forgive me that I write here my cons to the left, but this is just adding this guy here, and I cleaned up my rule. So there's another observation we can then make, that we have essentially right now only 2 languages, structural and linear. And this is a very important question. How could I have also applied? Okay. How could I have other substructural languages? Maybe I could even have 2 different kinds of structural languages in the system. Okay. Maybe that would also make sense. Because in some sense what we're doing is we're looking at the interoperability, in this case here, between a linear and a structural system. Okay. But only 2 languages. Okay. So the question is, could we actually generalize this in some form? So an important observation when people looked at the category theory semantics of this system was done by Brigitte. And he observed that that in this category theory semantics, the Bang modality is actually splits into 2 parts. Okay. So I'm going to give you the syntax for this because I've been talking about syntax all along. So I have a board. I have all my words. No, I think that's. So he observed essentially that you can go between these 2 using what he called an adjunction. Okay? And essentially that means that our language, okay, I should maybe say one more thing. The reason we don't want to do this with Bang is, so Bang is great. Okay, but that means how do we embed A implies B into this language that I have over here, which has Bang and then lolly. And the translation would normally say, well, you Bang A, okay, and you do a lolly B. So because in the intuitionistic case, when you made an assumption, A, we wanted to use it more than once. Okay, and the whole point was that we wanted to have intuitionistic things, or traditional things, structured things, and things that were linear, but we didn't want to duplicate this function space. We need to somehow embed it. And clearly, right, if I write these functions, I can use this assumption multiple times. So how do I use things multiple times in the setting? Well, I can. So there's an embedding of intuitionistic logic into the system. And you can show that everything that was provable in the intuitionistic setting is provable in this new formulation with Bang. So from a proof theoretic point of view, people were happy because it preserves provability. But the problem is that these programs look actually quite different because these programs now have this, have these extra rules in them. So the proof term for Bang is literally Bang, and this here is a let Bang elimination form, so you have these kind of additional stuff in your programs, so you're not really writing the programs that you used to write. So what we want to do is actually not only preserve provability, but preserve the structure of these proofs. And that means we preserve the programs that you've been writing all along. Okay? So we want a program that you've written, essentially with propositional typing, propositional logic, to be sensible in this system, and without rearranging the types and without rewriting your actual program. And we want to do that such that we're not duplicating all these rules, okay, but we still have a constraint system to begin with. And the third objective is that we can generalize it to any memory. So I'll give you a quick idea how to do this. So I'm going to do this by defining my proposition A, okay, where M can be structural, S for structural, okay, or L, okay, for linear, for now. Okay, and I will have, since when you write the function space, yes, okay. Okay, we'll have to agree on the symbol, but essentially when you write here in S, it means it's your traditional function space. If you write an L, it just comes from an L language, then it's linear. And in particular, okay, we'll have ways of going between these levels. Okay, so we have a way of embedding linear into structural. So that's an upshift. So the overall thing lives in the structural world. And we have a way of embedding a structural proposition in the linear world. This whole thing lives essentially as a linear proposition. And the nice thing about this view is that you actually now have a judgment or characterization for this judgment valid. So I think somebody also asked, oh, why don't I have a judgment for valid, for validity? Okay. I have assumptions that are valid, but I don't have a judgment that says it's valid. But with this formulation, actually we do. So far, I've only talked about two. But now we'll have a second judgment, which is valid. And I'll give you the two rules for it. So the upshift essentially tells you you can go from a structural setting to a linear setting intuitively. And so we have some delta here. And we're going to have here a structural proposition. That means we're shifting up a linear proposition. And since structural propositions are valid, we're making a judgment about a valid proposition. Okay. And under what condition is this true? Well, it is true. Okay. If A is linear, so it's linear, it means it's true. And we need to know that it actually doesn't depend on any of the, it really is the same kind of assumption. So essentially the assumption we have that delta is greater equal to S. So it is either, it is only containing valid assumptions. So that's what it says. This solution says delta okay, only valid. And the elimination rule is going to be opposite. It essentially says I have here delta, and I have here S and that is valid. I can go to true. So it closes the linear part, so it's going to be true. And again, we need to know that delta contains only valid. Okay. So it allows you to go between these two. And the downshift is the opposite. So downshift says you have something that is structural. And so I'm going to write a little S here saying it's actually only containing structural assumptions. And it's valid. Okay, so this must be an S, because otherwise it doesn't make sense. Then you can use it in the linear setting. Shift it down to true. And the usage of it is essentially a net elimination form. So we have that. We have here something that is linear. Okay, so that's linear. So that's true. Okay. We have some assumptions. Okay, so we have here some. And then we add it to our list of assumptions. Okay. AS, we think it's valid. And we continue to prove that C is true. And then we combine the resources to prove that C is true. So now we have essentially literally go between validity and truth. And you might say, well, doesn't this look like my bad rule? Not quite. So the bad rule looks a bit like this. Okay, so start with A being true under no other linear assumptions. Okay, so this is only dependent on the structural assumption. But here we have, but in fact, what it turns out is that we need to go between these two levels. So the bag will be actually an up, this is actually an A, it has an upshift and a downshift. And it can be modeled, then you can derive the rules from your system. So, it means also you can model box modality in the system. And you can generalize what I wrote here, SNL. There's nothing that requires me to write SNL in my grammar. Like that. There's nothing that requires me to be SNL. All I require is that S allows more structural properties than whatever I write L. Okay. So I can always go from, I have essentially a free order between S and L. Okay. I use structural and linear, so that was empty and it had a weakening and contraction. But it would be fine if you have weakening, contraction, you have contraction. Or weakening, contraction, you have weakening. Or you go from weakening to something that doesn't have any. So you get a whole set of languages that you actually characterize. Yes?
What if you had a lattice where, like, this arm only has weakening, this arm only has contraction?
Yeah, so we have a preorder. Okay. And some systems, so family Kata system, which is closer to the category theory semantics, you have indexed this language with another category theory, so then you have even more expressive power. But we found the preorder to be a good sweet spot that it is easy to check in practice. But there's many variations you might then aim to explore. Okay, so for example, you might say, oh, well, I don't want to have a function space in my language S, okay, which has here, this function space here exists in linear and in structural. Maybe I don't want it. How could I do this for polymorphism? How could I do this for dependent types? Okay. And more generally, what is the computational interpretation of this? Let me finish with 3 minutes because I'm already running over. And then I'm happy to take any questions. I'm around all afternoon. Okay. I'm going to the market. That's all fine. But I want to sort of conclude with two remarks. So the computational interpretation, what we've used this for, is essentially actually to model foreign function calls between two languages, okay? Where you want to sort of think of SNL as two languages, M and K, okay? And M can ask K to actually execute a particular program, a program that makes sense for K. But in order to do that, right, these two languages might not have the same representation of natural numbers. So you need to actually write a program here that says, okay, I can actually port my natural numbers to this K language. And what it turns out is the interpretation of these downshifts is sort of like building a pointer structure of allocation that traverses sort of the representation of natural numbers. And then, and this is sort of a notion of splicing syntax together. So when you do a foreign function call, you write a program that basically says, move my natural number over to the other language. I still retain a pointer to that representation here in my M, but it lives really in K. Then I can make my call in K. And in order for this guy, right, that asks this language to execute it, to import it back, they need a function that basically allows them to read from that pointer and import it back to its representation. So there are these conversion functions that we can write that basically work on all these downshifts. And then you have a way of modeling foreign function calls. The upshift is interesting because it actually gives you a very nice way of splicing code fragments together without going through a letbox formulation like what we see with the DOS modality. And so it gives you a way of more like clump-based communication or code-based communication. So this is related to suspension, okay, of code. We're suspending the code that lives here in this language L or K while working in this language S. And here we're going to force it. So now you have a much lower, you have much more control. You have a similar control in callback push values. Somebody mentioned callback push values to me, and you have heard about this. But here you actually have it for N languages. So it's really quite different. And in operational semantics, it's different. So if you're interested in that, there's a paper last year at FSCD together with Frank Fenning here, my student, Brigitte and Sophia Rocha. And so that gives an introduction to this natural reduction system. And since then, we also explored its actual uses for example, interoperable programming. So to conclude, so what I hope I have given you is a bit of an idea of how we can use this judgmental view to characterize logic, and how this can also inform us about computational properties. So in particular, you've seen these local soundness and local completeness properties we have in the logic that give rise to the reduction in our computational language. And that these local soundness and local completeness properties correspond to properties like time preservation or subject reduction in the language world. And then we sort of looked at beyond propositional logic. We looked sort of at mode logic as a way of talking about different kinds of programs. Things that were in the box, we can think of the syntactic structure of the program, so for instance code, and the things that were outside of the box that were the program that actually was doing the generation of such program. And the judgmental view was allowing us to sort of characterize this by sort of adding this distinction between validity and truth. And something that was true forever, that was valid, and things that were true, that was here right now. And today I was sort of revisiting this distinction by sort of saying, okay, now we make this distinction between something that are structural, they are true forever, okay, because we can reuse these assumptions as often as we like. And the linear assumptions, they are sort of our ephemeral assumptions. And since we don't want to sort of keep adding, right, more and more context to reason about FI, another linear language, another structural language. We don't want to have like a gazillion of these contexts. We want to sort of have a compact representation between them. We want to have a way of going between these languages in a nice way while preserving these structural properties. And that kind of allows, that would bring us to these shifts. And that give us sort of these ideas of shifting sort of from one language to another and giving us sort of this migration control. So I want to thank Zina, who's there, for inviting me. Okay, and I want to thank all of you for bearing with me for another 12 minutes. Okay. I think we all deserve now a good break, good lunch, maybe coffee at the market. I don't know what your plans are. And I hope you have a great time next week. It was really a pleasure to teach here and see all your brains at work. Okay, this is awesome. And I hope to run into you at any of the conferences over the next years. So, and hear more about what you're doing in your PhDs, postdocs, okay, and maybe some of you are faculty. All right.